Welcome back. In the previous section, we had looked at the area problem and the tangent line problem, and the solution for both hinged on us coming up with things where we could let something get close to zero. For the area problem, it was the width of our rectangles, and for the tangent line problem, it was the distance between the x values for our points. So of course that means we need to come up with a way to discuss what does it mean to be close to zero, or what does it mean to approach zero. And that's the topic of today's discussion. We're going to look at limits, which are a way of talking about what happens as we get close to some value. If we take a look at the function that we have over here on the left, of this arrow that I've drawn, you can see that it's a rational function and its denominator has an x plus 3 in it. So for sure, x cannot be negative 3. So if you said, what is f of negative 3? The answer is undefined. So for this function, there's nothing I can do to say, well, what would happen to the graph at that point? But I could still talk about what happens to the graph of that function near that point. So that's what I've done here in the little chart below. I've taken my x values and I've looked at values that are a little bit less than negative 3 and values that are a little bit bigger than negative 3. And then I've asked myself, what are the y values that I get for those values? So I can see that if I'm looking at values that are a little bit less than negative 3, my y values get a little bit smaller but seem to be tapering off to around 8 as we move our way to getting closer and closer to negative 3. And for values bigger than negative 3, it looks like my y value gets bigger and bigger and sort of tapering off and getting closer and closer to 8. So although there's nothing happening here at negative 3 at all, so there is no point on my graph at negative 3, I can say that as our x values are getting close to negative 3, that the y values are getting close to 8. So you could just sort of casually say then that f of x is getting arbitrarily close to 8 as x approaches negative 3. Arbitrarily close in the sense that if I got values of x that were even closer to negative 3 than the ones that I did, I would have y values that would be even closer to 8. So if I continued and looked at, let's say, negative 2.999999, the y value that I would get for that should be even closer to 8. And same thing with values that are a little bit less than 3. If I use something like negative 3.000001, I'd have something that's even closer to 8. So in other words, our function will get as close to 8 as we'd like for its y values as x is getting close to negative 3. And so what we're really saying here is this, that for our function, the limit of our function as x approaches negative 3 from both sides, from the left side and the right side, is 8. And this is how we would express this idea in symbols. We'd say the limit as x approaches negative 3 of our function is 8. So in other words, as the x values are getting close to negative 3, the y values are getting close to 8. And the getting close to negative 3 is getting close to negative 3 from both sides, approaching from the left and also approaching from the right. So for a limit to exist, we need to be able to approach that x value from both directions, and our y values have to get closer and closer to some real number. Now, the fact that this function doesn't have anything going on at negative 3 at all is not a problem. And in fact, what happens at negative 3 is really irrelevant, because when we're talking about a limit, we're talking about what's near to that x value, not what's at the x value. So I've got myself a little piecewise defined function here. And I've got this function's limit as x approaches 2 that I'd like to find. And I'm going to do that by graphing this function. So if you're taking a look at it, you can see that this is the graph of a parabola. It's got a y-intercept of negative 4. If you factored it to find its x-intercepts, you'd find that this factors as x minus 2, x plus 2. So should have x-intercepts, or would normally have x-intercepts at negative 2 and at positive 2. Except at positive 2, it doesn't have an x-intercept because at positive 2, the y value is actually something else. So when we're actually at positive 2, the y value is positive 3 for our function, but the parabola would get close to having an x-intercept. What we have is a parabola that will go through negative 2 and goes through its y-intercept, and it'll get close to having that x-intercept of 2 that y equals x squared minus 4 normally would, except once we get to 2 itself, we jump up to our y value of 3, and then once we leave 2, our graph continues on doing the same thing, doing its little parabola business. So this is the graph of our function f of x that we've drawn here. And for this, I can say the limit as x approaches 2 definitely does exist. We can approach 2 from both sides, and also what's happening as x approaches 2 from both sides is the same thing. So as we're getting close to 2, whether we're getting close on the left side of 2 or the right side of 2, either way, the y values are getting closer and closer to 0. So the fact that the y value is something completely different at 2 is completely irrelevant to us. I would say for this that the limit as x approaches 2 for our function happens to be 0, because as we approach 2 from the left and as we approach 2 from the right, the y values are getting closer and closer and closer to 0. The fact that the y value at 2 is 3 is irrelevant to us. The fact that those two things are different, though, does have an impact on what the graph looks like. So the fact that we've got what looks like a little hole in our graph with a little skip above it, that's coming from the fact that f of 2 and the limit as x approaches 2 are not the same thing. We're going to talk more about that in the future. But for right now, the key idea is for a limit to exist, the y value has to be approaching some finite real number as we approach our x value from both the left and the right side. So as I said, for the limit to exist, you need those things. Number one, the y value has to get close to a real number. And of course, something like infinity is not a real number. So if you have a graph like 1 over x squared, where on the left side and on the right side of 0, the y values are becoming infinitely large, that would be an example of something where a limit doesn't exist. The y values are not getting close to a real number. The y values are becoming infinitely large. So that's one thing we need. Our graph has to have the y values approaching some real number L. And x has to approach our c, so we're doing our limit as x approaches c. As x approaches c, it has to be able to do that from both directions. So if we have a graph where you can't approach from both directions, then you would not have a limit. So maybe f of x doesn't approach a real number as x approaches from one or both directions. That could happen. And the reason could be maybe because the y values are becoming infinite, or maybe it might be because there is no graph, so the y values aren't approaching anything. You might also have that what's happening on the left and the right side is disagreeing. So for our limit to exist, f has to approach the same number as x approaches c from both sides. So if the y values are getting close to something on the left and a little something different on the right, that would be another case where the limit doesn't exist. Or maybe you get a function that doesn't actually get close to a real number, it just oscillates. Maybe it's alternating back and forth between two numbers. There's all sorts of options of ways in which limits could not exist, but that's the key thing. For a limit to exist, our y values have to approach a same real number as we're approaching our c, our x value, from both sides. So we have some limits we're going to investigate, and I'm going to do this by thinking about graphs for these functions. And so we want the limit as x approaches pi over 2. And I know for the graph of the tangent function that it's got a bunch of vertical asymptotes. And so in particular, it has a vertical asymptote at pi over 2. So if you said, what is tangent of pi over 2? I would say nothing. However, it does have a graph to the left of pi over 2, and it does have a graph to the right of pi over 2. So here I've just drawn just the part of tangent near pi over 2. And I can say that for this, the limit wouldn't exist for lots of reasons. Number one, what's happening on the left for the y values is not what's happening on the right. They are not both approaching the same thing. But also, even worse, they're also not approaching real numbers. So for many reasons, I would say that this limit does not exist. The limit as x approaches pi over 2 for tangent does not exist. So it doesn't exist because the y values aren't approaching real numbers. They're not approaching the same real numbers. Even though we can approach pi over 2 from the left and the right-hand side, because we're not approaching the same real number, the limit does not exist. Okay, a little piecewise defined function. So I've got this x divided by absolute value of x. And if I were thinking about redefining this for a minute, I might notice, of course, I'm just going to make a note to myself that this function definitely is undefined when x is 0, because when x is 0, you'd have 0 in the denominator. So just like the other previous example, tangent, where tangent of pi over 2 did not exist, but we could still talk about limits. For this function, it does not exist when x equals 0, but we could still talk about it using limits. So now, if I'm thinking about redefining this as a piecewise defined function, and the reason I'm doing that is because the absolute value function does two different things. If the inside of the absolute value was already positive, then the absolute value wouldn't do anything. So in other words, if x were greater than 0, then you would have just x divided by x, or in other words, the y value would just be 1. And if you're talking about being in the part of the graph where the inside of your absolute value is negative, or where x is less than 0, then the absolute value will change the sign. So when you put in a number x, it'll give you the opposite of x. It'll give you negative x instead. And that would make this thing no longer a negative number. But here, x divided by negative x will be a negative number. That'll be negative 1. And then we will have something where the graph looks a little something like this, where on the right side of 0, you've got a horizontal line with a y value of 1, and on the left side of 0, you've got a horizontal line with a y value of negative 1. So on the left side, you're approaching a number, you're approaching negative 1, and on the right side, you're approaching a real number, you're approaching positive 1, but the left and the right sides are not agreeing on what they're approaching. They're not approaching the same real number. So for this one, again, the limit, I would say it does not exist. So this one, you can approach x equals 0 from both sides, from the left and the right. The problem here was the left and the right side were approaching real numbers, they just weren't approaching the same real number. Okay, x approaches 0 for square root of x. This one we can see what the problem is right away just by drawing my graph of square root of x, doing a little sketch of that. I know that my domain for square root of x is all the numbers 0 and larger, so I can get close to 0 from the right side, and I can say definitely the y values are getting close to 0 there. But if you're talking about on the left side of 0, there are no y values going on, so there's nothing for me to approach. So I can't even approach on my function as x approaches 0 from the left, because there is no function on the left side of 0. So for this one, because you can't approach 0 from both sides, I would say the limit does not exist. If we were talking about a point that was somewhere in the interior, so for example, if we were talking about the point 1, 1, I could totally talk about x approaching 1, because, yep, you are approaching an x value from both sides. But for this function, if we're talking about 0, on the other hand, too bad. You are only approaching it from the right side, not from the left, and that's because, of course, the domain does not have anything on the left of 0. So as a result, the limit does not exist. Okay, so this one's sort of a funny function. It is a function where you do one of two things. You either are going to get a y value of 1 as your output, or a y value of 0 as your output, depending on whether the number that you put in was rational or irrational. So, for example, if you put in 0.2, that's a rational number, so the output would be 1. Or if you put in a whole number, that's a rational number, or 0, or something like -3/4. All of those would have y values of 1. But anybody who's not a rational number, so irrational numbers like pi, that would have a y value of 0. Or our favorite constant e, that would also have a y value of 0. Or square root of 2, that would also have a y value of 0. So what we're going to wind up having, if we're thinking about just as a graph, is a bunch of disconnected points. So if I really like zoomed in, so let's say out here, this is like 0.00001, and way out here is -0.00001. You'll have tons of little points of zeros, all those irrational numbers, but you'll also have tons of points with y values of 1, all those rational numbers in between. And one little fun fact, and this is something that's just the nature of real numbers, is that if you're looking at any interval, no matter how small it is, there's always going to be some rational numbers and some irrational numbers in that interval. So that means you're going to have some zeros and some ones for y values. So if you're talking about approaching 0 from both sides, the y values aren't really approaching anything. They're just alternating back and forth between zeros and ones. And that would be whether we're talking about x approaching 0 or actually really x approaching any other number, because the same premise would be holding true for any other number you'd be interested in. Any interval you're looking at, there's going to be things with y values of 0s and y values of 1s. You're not approaching anything at all. So for this one, I would say, again, the limit does not exist.